Colligative properties are the properties of a solution or a solvent that change due to the concentration of a solute. So as the concentration of the solute changes, it's going to affect the property. So we have 4 different colligative properties. We have boiling point, freezing point, depression, vapor pressure, and osmotic pressure. And all 4 of these properties are going to change depending on the concentration of solute within the solvent. Now over here, first of all, we have the freezing point depression. Now here we can see that we have pure water, and when we freeze pure water, it turns into ice. Now if we add some sort of ion or solute to our pure water, for example, we take salt water and we try to freeze it, we'll first end up with this slushy water where it's half turning into ice but half water. And then finally, at a lower freezing point, we get ice. Why does that happen? Well, when we have these solutes within our solvent, so let's say that the blue represents the water and the orange represents some sort of solute. When the solute exists in between the solvent or the water molecules, it's preventing those water molecules to interact and form those strong bonds to freeze with one another. Essentially that hydrogen bonding, right? So if these ions are in between, preventing that hydrogen bonding or that other type of bonding in general to get to that ice structure, it's going to take a lot more colder temperature or a lower freezing point to try and get to that very complex ice structure. So essentially, if you have a higher solute concentration, the more solute you have, the more disturbance you're going to have in between your solvent molecules, and it's going to require a lower freezing point. So it's going to get colder and colder to try and freeze your solvent because those solutes are inhibiting that bonding between the solvents. So this is the equation that represents the freezing point depression. So this is the change in the final temperature, and we have the Van 't Hoff factor. We have this K constant, and that K constant is going to be different depending on which solvent we are talking about. And then lastly, we have the molality, and remember that molality is different from molarity in the sense that molality is moles divided by a kilogram of solvent, whereas molarity is moles divided by the liters. So next up, we have boiling point. So boiling point, when we talk about it as a colligative property, the more solute you have, the higher the boiling point. And the reasoning behind boiling point is a little bit more complex than our freezing point depression. So whenever we want to boil something, let's say we have a solution, and within this solution we have dissolved a bunch of salt. When the water evaporates away in our container, we are going to be left with a bunch of NaCl. And it's going to form bonds with one another, and it's going to be more organized. Whenever we refer to something as more organized or disorganized, remember that we talk about entropy. So when the ions are dissolved in solution, the ions are dispersed very randomly. So we have a high entropy. And remember, entropy simply is synonymous with randomness. So when the NaCl is dissolved in solution, it is very random, so your entropy is very high. But when that water is evaporated off and you're left with that NaCl simply at the bottom, and it's no longer dissolved in its ions, it forms that NaCl molecule, your entropy has decreased. Now we know in the universe, a decrease in entropy or order is not very favorable. The universe favors disorder, so it favors high entropy. So going towards lower entropy is not favorable at all. And that is why we require more energy to evaporate that water and to be left with that solute. So the more solute you have, the more disorder you'll have in the solution. And if you want to evaporate that water off, it's going to require a higher boiling point, because the more solute, the higher the entropy. And if you get rid of the water, the lower the entropy will be. And the universe does not favor lower entropy. It wants to stay with the high entropy. So that's why the more solute you have, the higher the boiling point. And you can actually calculate that change in temp with the same equation as before, but we've replaced it with the B's instead of the F for freezing, and we've gotten rid of that negative sign, because remember, when we're talking about the freezing point, we're talking about really low temperatures. So that's what the negative represents, whereas over here we don't need that negative, because the boiling point is going to be positive because we're adding in energy into our system. So our third colligative property is known as vapor pressure. Now, it's very common to confuse vapor pressure and boiling point because they go together, like hand in hand, but it's important to remember the key differences between the two. So let's say we have some sort of a liquid, and we start boiling that liquid. There's going to reach a point where we start seeing these little vaporizations coming up, which we refer to often as this steam. So we have this vaporization. Now, if we take a isolated closed container where the vaporization of the solution of that liquid, as the vapor moves up, and since it's a confined system, that vapor will eventually have to liquefy and condense and come back down. Once we've reached that equilibrium of vapor going up, condensing, and coming down, that's referred to as vapor pressure. That's the pressure that's exerted by that liquid when it is boiling. So vapor pressure, essentially, it depends on the vaporization and that condensation. It does not refer to the temperature at which the liquid boils. So going back to this diagram over here, we can see we have the liquid and we have the phase transition going from liquid to gas, and we get these vapor particles, and we refer to this as vapor pressure. So when the liquid is boiling, its vapor pressure is going to be equal to the external pressure that it experiences. So to put in simple words, the solute particles, when we increase that solute concentration within a liquid, the solute concentration is going to obstruct the path of the liquid, or it's going to be in between those liquid particles. And if it's obstructing in between those liquid particles, it's going to reduce the likelihood of evaporation occurring. And if we reduce the likelihood of evaporation occurring, we're going to have less vaporization. If we have less vaporization, then we're going to have a lower vapor pressure. And I hope that makes sense. So when we add the solute particles, we are obstructing, or we're coming in between those liquid particles, and we're reducing the likelihood of that evaporation. And if there's a reduced evaporation rate, then we are going to be lowering that vapor pressure. Now we can actually calculate our vapor pressure once we've added in the solute, and that's actually going to be the original vapor pressure when there was no solute, and this XA value represents the percentage of solvent in the new solution. And with that, we can calculate our new vapor pressure. So once again, to summarize, when we have a high solute concentration, we have a low vapor pressure because the solute gets in the path of the liquid. Lastly, our fourth colligative property is osmotic pressure, and remember, this one is quite simple and straightforward. Whenever we have a high solute concentration, we're going to have a higher osmotic pressure on that side. So over here we can see that this red represents that we have a higher concentration of solute on this side. So the water is going to move over to the right side to equalize that concentration of both sides. So since we have increased the amount of water on this side to create that equilibrium of concentration on both sides, there's going to be a pressure exerted over here. We can refer to that as pressure X. And that pressure X is actually greater over here than it was originally. So the pressure increases as we add more and more solute, because we have more water moving to that side if we have more solute. So osmotic pressure, whenever we add more and more solute, we're going to end up with a higher and higher osmotic pressure because we get more water and more water. And remember that we're exerting pressure onto that system. So that is essentially all of our colligative properties.